this is our first community conversation, and we're very lucky to have Kerry Emanuel here. He's a professor at MIT, and he's written a book about climate change, so I'm really excited to see what you can share with us about this. So thank you very much for being here.
It's a great pleasure to be here with all of you tonight. I'm also on committees like the one that organized this meeting up in Maine, where I now live. And they became very active after the coast of Maine got slammed by two very rare intense storms this past January, which really put a big dent in the fishing industry and so forth. My perception is that in this country, all of the interesting action is happening at the level of towns like this one. The further you go up the chain, the less is happening at the moment. And maybe that's not such a great thing, and maybe it will turn into a great thing, because I think it's better than the top-down approach myself. But I'm not here to talk about politics tonight. If you want, in the discussion section, we can talk about possible solutions to this problem, if you like, but I'm really here to tell you about science. And before I start in on this, I want to say that I got involved in the science in the late 1970s. And I pursued an interest in climate simply because it's fascinating, like for the same reason that a lot of good scientists study the cosmos, right? There's no particular gain to humanity except a cultural one from studying the cosmos. When we were studying science, we studied science because it's fascinating, and it still is, and you have to remember that that's why people like me do it. And then, of course, because it has become important, we have to try a little bit harder to communicate what we do, and that's why I'm here tonight. Try to tell you a little bit about climate science. So the program for tonight is I'm going to give you a little very brief history, which all by itself is fascinating, of climate science, and talk about anthropogenic or human-made influences on climate. It all boils down in the way it affects us to what we call climate risks and how we're going about trying to quantify them. If you're going to come up with solutions to climate risk, you want to be able to say something about how much the risk might cost, right? You don't want to spend a whole lot more than that risk is worth, and you don't want to spend too much less either. So we're trying to get better at that. And then I'm going to end with a little discussion of hurricane risk here in Winthrop. I'm sure you'll be delighted to hear about that. Okay, let's talk about just the history of Earth's climate a little bit. This is a bunch of squiggles on a piece of paper that tell you something about how the climate has changed over the last 450,000 years. So on the left part of the axis, it's 450,000 years ago, going to the right, which is today. And you're seeing basically four records on here. The first two are proxies for the global temperature from ice cores in Greenland and Antarctica. Okay, so the two different ends of the Earth, if you will. And you can see that there are these periods where it's quite cold relative to today. And you can see that there are other periods which we call interglacials that are much warmer. This pattern goes back actually about 1 million years, okay? But you're just seeing the last 450,000 years of it. The bottom curve is different. It's a proxy for the volume of ice on the planet. This is a very fascinating story of geochemistry. By looking at the fossil remains of microorganisms on the bottom of the seafloor, it's possible to infer how much ice there was on land in the planet. Sounds pretty bizarre, doesn't it? If you want to know how we do that, I'm happy to talk about that a little bit. Okay? Well, you can see, well, the ice volume curve is reverse. Low is on the top, high is on the bottom, just so you can see how well correlated these proxies are. So there's no doubt that the Earth went through all these cycles of glaciation. One of the aspects of climate, and this is over 450,000 years, which geologically is nothing, of course. For us, it's a lot. Where was I going with this? And so if we turn the clock back to the peak of the last glaciation, about 20,000 years, this is reconstruction of what it looked like. If we were here 20,000 years ago, we'd be sitting here under a mile of ice. In other words, we wouldn't be sitting here. And if you could crawl out from under that ice sheet, somehow, you could walk from Winthrop to Cape Cod without getting your feet wet, because sea level was about 400 feet lower. Okay, so it's a lot of climate change. And as the ice melted, sea level came up. This is just a record at sea level. This is going back to about the peak of the last glaciation, 22,000 years ago, to today. Starting about 18,000 years ago, the ice started to go away. And with that, all the water ran off into the ocean, sea levels rise. And that's the sea level change from today in meters. So it's about 120 meters, which is about 400 feet. Okay, that's a lot of sea level change. Now you notice that starting about 7,000 years ago, the sea level stabilized. And probably not coincidentally, that's when human civilization began to develop, when we began to do animal husbandry, to do agriculture, settled down, because the climate was stable. And we've had a remarkably stable climate by the history of the geology of the planet for about 7,000 years. And we human beings are exquisitely finely adapted to that climate. So when people say, how do you know this is the best climate? By definition, it's the best for us because we're so beautifully adapted to it. So if it got colder or it got warmer, the climate changes away from this, we have to adjust, right, to that. And it could be bad either way. It's not like it's going to be better if it's warmer and worse if it's colder. It's just any change is not good when you're so finely adapted. This is 400 feet. And here in Winthrop, we rightly worry about 2 feet of sea level change. But by the standards of the past, it's not very much. Now, science has figured out why we had these ice cycles. It's not a mystery anymore. And it has to do with the fact, and I'm showing you a portrait of one of the mathematicians who was instrumental in this, Emanuel a Serbian mathematician who lived from the end of the 19th century to the middle of the 20th. And he, like a few of his predecessors, thought this had something to do with the Earth's orbit around the sun and the rotation on its axis. So the Earth's orbit around the sun is not circular. It's elliptical. It's nearly circular. But right at the moment, northern hemisphere winter, we're actually a little bit closer to the sun. It's not that variation of distance from the sun that's driving the seasons, but it does have an effect. And other cycles of the orbit were closer to the sun in northern hemisphere summer, and that makes for more extreme summers. That cycle is 100,000 years, and it's the big pacemaker of the ice ages. You might have noticed those spikes were about 100,000 years apart. Okay. But there are other things going on. The Earth's axis is tilted with respect to the plane at which it orbits the sun, and that tilt is really responsible for the seasons. It's a 23.5 degree tilt today, but it hasn't always been that. It wobbles like a top. And that wobble is on a period of about 40,000 years. Okay, so these are all natural things, and the rotation of the Earth on its axis also precesses like a top, which is responsible for the fact that sometimes the Earth is closer to the sun in northern hemisphere summer, sometimes it's northern hemisphere winter, or other times of the year. Now what matters about all this is how much sunlight comes into the high latitudes of the northern hemisphere, where the ice forms. So here's a really beautiful record. It goes back 1 million years. So that 1,000 on the left, this is measured in thousands of years, so that's 1,000 years ago, or 1 million years ago on the left. And there are 2 quantities that are shown on this graph. There is the sunlight coming into the Arctic, according to the mathematics of this man Milankovitch. That's in the red. And the black is the time rate of change of the composition, measured the composition of ice cores. And that rate of change of, I'm sorry, not ice cores, deep sea sediments, but they are informative about the volume of ice on the planet. So what you see is that every time you have a lot of sunlight coming in, there's a high rate of change of ice volume. It's actually going down. And when you have relatively low amounts of sun coming into the Arctic, it's the other way around. So this is pretty convincing proof that Milankovitch was right. We know why there were ice ages. And they will continue on, but don't worry, we're not due for another ice age for 30 or 40,000 years. We won't have to worry about that. But it is an accomplishment of climate science. You're hoping to live that long? We should be so lucky. But we have evidence of climate change on much longer time scales. This is a fossil of a pond from 65 million years ago, found near Edmonton in high latitudes of Alberta in Canada. And it wasn't in so much of a different position than 65 million years ago than today. There was some continental shuffling. We're still at high latitudes. Well, palms only grow in the tropics. You don't see palm trees growing in high latitudes except in people's living rooms sometimes, right? And so that's pretty good indication, and there are many, many others, that it was pretty warm at high latitudes. And we have evidence from all kinds of different techniques. This is what West Antarctica we think might have looked like at the peak of the Earth's temperature about 100 million years ago. Right? So that looks more like a tropical landscape. The Earth's climate undergoes pretty big variations on long timescales. On that timescale, it didn't have anything to do with orbital things because they're much, much faster. This is 100 million years. That's 100,000 years, that cycle. So what caused that? Well, our best guess is that it's related to carbon dioxide in the atmosphere. So what you see here is a chart going back 70 million years now, so we're on a very different time scale, of reconstructions. By the way we do this is a fascinating story I wish I had time to tell you. It's a lot of interesting science. Estimate of the Earth's global mean temperature going back 70 million years ago. So as I said, it's going to reach a secondary peak around 55 million years ago, but it was actually warmer even before that. And then it started to slowly cool off. Up until about 35 million years ago, there was no ice even in Antarctica. About 35 million years ago, ice began to develop in Antarctica, and the Earth has sort of slowly cooled over this time. And this is when we entered the period of these rapid fluctuations that we call the ice ages. The bottom chart is showing estimates which have a lot of uncertainty and a lot of scatter, but estimates of carbon dioxide content over that same span of time. And you can see there's a rough correspondence. It's not perfect between atmospheric CO2 and temperature on these timescales. It's not a big surprise because we've understood the physics behind that for well over 100 years. And that brings me to the greenhouse effect. What is it? Actually, it's very little to do with greenhouses. We're stuck with the terminology. And arguably, it was quantified by this dour-looking Irish physicist, John Tyndall, who built the apparatus. You see a sketch of there, which actually still exists. If you're in London and want to see it, you can go to the British Museum, and there it is. And what he did was to fill this tube with various kinds of gases. And then he would shine light of various different wavelengths through the tube and measure how much of the light came out the other end, which was a way of measuring how much of it was absorbed by whatever gas was in that tube. So if you were doing that experiment at the end of the 19th century and you didn't know anything at all, what would you do? You'd put in the most abundant gases in the atmosphere, oxygen and nitrogen. You tried nitrogen, nothing, no absorption. He tried oxygen, nothing. He kept going down the chain and ultimately discovered, as I'll show you in a bit, that this absorption of infrared radiation is mostly due to a handful of trace gases. So let me come back to the greenhouse effect. This is a cartoon of the Earth if it had no greenhouse gases. And we can sort of do a very simple calculation of what the surface temperature would be on that planet. So we have sunlight coming down. It pretty much goes through the atmosphere. Visible light does not get absorbed. I'm assuming there are no clouds in this particular world, okay? And it's absorbed by the surface. And what would happen is over time, the surface would just get hotter and hotter and hotter. but it doesn't because it starts to emit radiation back to space. It's infrared radiation. Everything that has a temperature, which is everything, emits infrared radiation. We all emit infrared radiation, which is why I can see you at night if I have infrared glasses, right? The system comes into balance when as much energy is going out to space in the form of infrared radiation as is coming in from sunlight. And it's a very simple law about how much infrared radiation is emitted, and it depends very strongly on temperature. The hotter it is, the more it emits. So it gets hot enough to emit just enough infrared radiation. And if that were the case, if there were no absorbers in the atmosphere, it's very easy to do the calculation. The Earth's surface temperature would be, hold about 18 degrees below 0 centigrade. Very cold, the planet would be frozen and we wouldn't be here to talk about it. So they knew in the 19th century, even before John Tyndall's time, that there was something else going on, that the atmosphere had to be absorbing some of this heat coming up from the surface. And it does. And so when we allow for that, what happens is some of the infrared radiation going up is absorbed by these trace gases in the atmosphere. Now, if that's all that were going on, right, the atmosphere would just get hotter and hotter and hotter. And would never come to equilibrium. But I just told you everything that has temperature emits radiation. So those gases emit infrared radiation, up and down, and sideways for that matter, okay? So if you're standing on the surface of the Earth, you're getting two sources of radiation. You're getting radiation directly from the sun, in the form of mostly visible light, and you're getting back radiation from the atmosphere, and in reality, the clouds in the atmosphere as well. Those are greenhouse agents. So now you have to get hot enough, not just to balance the sunlight coming in, but to balance this infrared radiation coming down from the atmosphere. And when you put in the actual composition of the atmosphere, that makes the surface temperature about plus 15 degrees C, which is much closer to what we observe the average temperature of the Earth to be. Okay. That's the greenhouse effect. It's just the fact that the Earth has to get warm enough to balance not just sunlight, but the back radiation from the atmosphere. The back radiation is 24/7, unlike the sun. It's a very powerful effect. In fact, in reality, we get twice as much radiation from the atmosphere and clouds as we do directly from the sun, which is kind of interesting. It's a very strong effect, this greenhouse effect, and that's why we're here to talk about it. So when Tyndall went down through this list of things, he tried the next most abundant gas is argon, and that was nothing. He didn't get any effect there. He's beginning to wonder about whether his instruments are working, but then he puts in some other gases, water vapor, carbon dioxide, nitrous oxide, and later on, of course, we looked at other gases as well, and he found bingo. Those gases absorb an awful lot of infrared radiation. And they're responsible for the greenhouse effect, even though they don't make up a huge proportion of the atmosphere. So here's a pie chart of the composition of the atmosphere. 78% is nitrogen, 21% in round numbers is oxygen. You probably know that from chemistry in school. Argon is 0.9%. Water vapor, which as you know varies a lot, like it's pretty humid today. 0.25%. That's its average concentration. There's not a lot. It's not relative humidity we're talking about here. We're talking about the proportion of water vapor compared to all of the other gases in the atmosphere. And carbon dioxide is 0.04%. It's that tiny little sliver. Can you see it? Probably not. It's a tiny, tiny little piece of the pie. But what Tyndall discovered, somewhat to his amazement and that of his compatriots at the time, was that little green and orange slice makes the difference between a habitable planet and one that isn't. But it's even more spooky than that in a way, because water vapor is a bit of a special greenhouse gas. It's the most abundant by far. It's a lot more abundant than carbon dioxide. It's therefore the most important greenhouse gas, but water cycles very quickly between the surface of the Earth the oceans, basically in the atmosphere. So water molecule may stay in the atmosphere on the average for 2 weeks. So it's not, you can blow up a huge water balloon and double the amount of water vapor in the atmosphere. That'd be a mighty big balloon, but you can imagine it, right? A couple of weeks later, everything would be back to normal. So our emissions of water vapor make no difference at all on this scale. So water vapor, it turns out to be controlled mostly by temperature. And it's a feedback. If you make the atmosphere warmer, it can hold more water vapor. It's a greenhouse gas, and therefore it amplifies that warming. But carbon dioxide and some of the other gases stay in the atmosphere for a very long time, hundreds or thousands of years. And so climate is really being controlled by these long-lived greenhouse gases, the most important of which is carbon dioxide. But altogether, they comprise 0.04% of the atmosphere, hardly any of it. All right? So it's an amazing fact that our climate is strongly controlled by a tiny fraction of the mass. If it's the winter time and we're sitting in this room and it's cold outside, there's a thermostat in the back. But in the old days, it was probably a mercury-driven thermostat. And that tiny little bead of mercury would be a tiny, tiny percentage of the mass of this room, but it's controlling the temperature. So it's kind of a thermostat effect. Kind of an interesting thing. There's nothing controversial about what I'm saying here. This is science that really was well known by the end of the 19th century. Nobody in my field debates these points. Now, this Swedish chemist, Svante Arrhenius, who looks even grimmer than Tyndall. I don't know what is it about climate science. After looking at these pictures, I try to smile when I give my talks. I try to break the pattern. He was the first to worry toward the end of the 19th century that burning fossil fuels would tangibly change the composition of the atmosphere. And he did some calculations, and this was done in a time when we had no satellites, we had no really good way of even measuring carbon dioxide content in the atmosphere. But his calculations suggested, we should go back to the bottom of this, that if we were to double the carbon dioxide content in the atmosphere, we'd raise the surface temperature of the Earth by 4 degrees C. This is a prediction that was updated in 1906, 120 years ago in round numbers. And that's well within the uncertainty of our current understanding or projections of how much we can change the temperature of the planet by putting more of this important greenhouse gas in. Right? This is very old science. There's nothing particularly new about it. And we can ask, was Arrhenius right? Because since then we've gotten very good at measuring the carbon dioxide content, and we can look at bubbles trapped in ice cores to get carbon dioxide going back in time a long way. And of course, we've been measuring temperature fairly accurately since the end of the 19th century. So this graph shows the global mean temperature relative to a baseline in blue, and the red is the natural logarithm of the carbon dioxide content. It's a technical thing because the radiative effects of carbon dioxide go up more like the log rather than first power. It's actually not a big difference. So you can judge for yourself. Did he make a good prediction? Well, clearly there's a lot more going on in the temperature than just the carbon dioxide. There's lots of variability from year to year. Some of it's perfectly random, caused by weather, if you will. Some of it is volcanically driven. And volcanoes tend to cool the climate. And some of it's driven by variations in the sun itself. But for the most part, you can see that that's a pretty good prediction of what's happening. What I want to disabuse you of, because it's unfortunately something that journalists often get wrong, is that everything we know about the climate depends upon huge, complicated models that nobody understands. It's just not true. If we didn't have any of those models, we'd be very confident about this kind of relationship. Right? It's not to say that models are useless. I'll come back to that in a minute. Okay? It's just that a lot of the foundational physics of this doesn't depend upon big fancy models. I get my first year graduate students to do some of these calculations. It's not even that difficult. And no computers. Well, we can go back in time with carbon dioxide, much further back. This is going back 1,000 years, or to 1000 AD. And this is from ice cores. It shows measurements of carbon dioxide. And it was about 280 parts per million by volume until the dawn of the Industrial Revolution, and it started to sail up. So we did that, right? There's no question about that, because the exact chemical composition, the isotopic composition of the carbon dioxide coming from fossils is different from that naturally exists in the atmosphere. So we know it came from that and not from something else. That's a hell of a spike, okay? And of course, it's continuing over time. And, well, it's literally off the chart, right? I have to keep revising this chart so often that I forget to do it. Here's a record of Arctic temperature in the high latitudes of the northern hemisphere going back to about 2,000 years ago. And you can see a slow cooling trend, which is part of this Milankovitch natural cycle. If we had interrupted it, that part of the world would be slowly cooling down, getting us ready for the next ice age. But we did interrupt it. And again, starting at the dawn of the Industrial Revolution, around 1800, the temperature soared there, okay? And we see all kinds of evidence of that. And again, here's a record going back now 800,000 years of carbon dioxide trapped in ice cores. There are natural variations that are in sync with the ice ages. In this case, mostly it was the temperature driving the CO2 and not the other way around. But look what we did to the end of that record. We really put a hell of a spike. So we now have more carbon dioxide in the atmosphere than we've had for at least 3 million years. And given that that's the most important greenhouse gas in terms of its ability to influence climate, it's a little spooky, all right? We're taking a risk here. And the question is, can we do better than just to say that? Can we put numbers on it? Can we put some uncertainty on it? What are the consequences? Are they not much? Are they serious? That's what we're trying to figure out. There are other trends. We've been able to measure the precise altitude of the sea surface with satellites for some years now, going back to the early 90s. And this is just the trend in sea level around the world as measured by satellite. And some of you might be surprised that the sea level isn't going up at the same rate everywhere. This is one of the things also that it's understandable mistake. Sea level goes up, it's like a bathtub, it goes up everywhere, it doesn't. There are places where it's falling. Like around Greenland, the sea level is actually falling. There are places you used to be able to bring boats into Iceland you can't do anymore because the sea level is falling there. But on average, it's rising. And it's another very fascinating story. Why is the sea level going up in general? Well, the ice caps of Greenland and Antarctica are melting, water is running into the sea. Changing winds. Winds pile up water in certain places and take water away from other places. Change the pattern, they don't change the average. Changing ocean temperature. Seawater does expand a little bit when you heat it, and it's important enough that it's actually responsible for a lot of the change we've seen over the last few decades. And the weird one is the reason that the sea level is dropping around Greenland is that the ice, like every mass, has gravitational attraction. And the ice mass, Greenland, slightly pulls up the sea around it. It's attracting another mass. As the ice melts, that attraction goes away, and the sea level drops. It's a remarkable thing. By measuring the sea level, you kind of know how fast Greenland is melting. Because we're measuring the change in the mass of ice. The oceans are becoming more acidic. This is a problem as well. And that makes it very difficult for organisms, microorganisms, and also things like mollusks to build shells. We know that from doing experiments in tanks. So that gets to be a risk and it's directly related to carbon dioxide. It's not so much to do with climate. So it's another thing that unfortunately we have to worry about. We do have climate models, and I'm not going to talk about them very much in this talk. This is an attempt by running quite a number of climate models that to try to replicate this record by putting in all the things we think influence temperature, the CO2, variations in sunlight, volcanoes, and so forth. And you can see the black line is what was observed going back to 1900. The red line is sort of the average of all our attempts to model this with climate models, and the shading shows the scatter between the models. So it's a measure of the uncertainty of the models. The blue curves are the same thing, but we left out the greenhouse gases, and so it's just really the natural variations. And you see, you cannot capture very much of what happened since 1960 unless you put in these changing greenhouse gases. So that's one thing that we've kind of learned from models. So we go to the future. The sources of uncertainty, there are a lot of things we don't know, right? Because the scientists are supposed to, sometimes you think we're supposed to get up and tell you what we know, and I sort of try to do that. It's very important for me to also tell you what we don't know, or at least we don't know yet. Clouds are really important. They reflect sunlight, they cool the planet, but they're also greenhouse agents, so they're working both sides of the street. They're also emitting infrared radiation back to the surface and warming it. So exactly what kind of cloud, how high it is, matters. And they're really, really tough to deal with in models. Sometimes it could be very thin and still have a huge effect on sunlight. You know that, just from looking up at the sky. I mentioned that water vapor is a feedback. You warm the atmosphere, there's more water vapor. That's a greenhouse gas, so that amplifies the warming. But just how much it does that is got a lot of interesting physics behind that haven't been completely sorted out. The response of the ocean is really important. I haven't talked about that. The ocean transports a lot of heat. And aerosols, particles in the atmosphere, which you saw a lot of this summer in the upper atmosphere from the fires, and mostly from Western Canada. But there are natural aerosols, and they have and man-made aerosols that have an effect. So there are all kinds of things we have to deal with. And so when we put it all together, if you ask me how much will the world warm up if we double carbon dioxide, I can't give you an answer. I can only give you a probability of the answer. And this is what this is supposed to show you. It is actually made by running literally thousands of model simulations on people's home computers, people who volunteered to let climate scientists use their computers at home, remotely of course, when they weren't using them. That's how we managed to do a chart like this. It's a real grassroots effort to do climate. And so this is really just the probability that you'll see global warming of this magnitude in response to doubling CO2. So the most probable outcome is somewhere between 2 and 3 degrees. But there's maybe a 5% chance it will be less than 1.8 degrees. If we're down that territory, it's something we should just plain learn to adapt to, right? And it's probably not worth doing more than that if we can be certain it was down in that territory. There's a 5% chance it will be up above about 4.6 degrees, and that would be truly catastrophic for a lot of reasons. Okay. So then it gets to be, it ceases to be a question of science. We've done our job, part of our job, by showing you this. It's up to everybody to decide how much risk they want to incur for their kids, for themselves, and so forth. That's a political thing. But this is about the best we can do. You'd like us to be able to say precisely what the number will be, but we know enough to know we can't do that. Certainly not now. Okay? There are limits to our knowledge, and that's just, unfortunately, the situation. But depending upon what we do in terms of burning fossil fuels or trying to take them out of the atmosphere, right now we're on track to go well beyond doubling CO2 by the end of the century. So this is projections of CO2 concentration. Well, this is what actually happened, and this is projections according to different assumptions about how we're going to behave. So you can pick your curve, right? Nobody can predict how we're going to behave. Some of them sort of assume that we'll really somehow come up with a way of replacing fossil fuels or taking carbon out of the atmosphere, in which case we don't have to replace the fossil fuels. And some of them just say, well, we're just going to keep doing what we're doing, accounting for all the increased economic growth in the Far East and changes in population and so forth. This dashed blue line is doubling, and you can see we sort of cross that point by mid-century, and then depending upon what we actually end up doing, could go well beyond doubling. And this is just meant to show that whatever we do, if we don't learn how to take CO2 back out of the atmosphere, we're kind of stuck with the level of CO2 we have if and when we stop putting CO2 in the atmosphere. This chart shows what's projected to happen to CO2. This is going all the way back to 1800 and forward to 3000. So it goes rocketing up, and then we're just going to assume that at some point we turn it off and ask, how will the system behave? Obviously, it's unrealistic that we just turn it off, but we're going to assume that we do. And you can see that at first, the carbon dioxide drops pretty quickly, like over 100 years. But then it takes thousands and thousands of years for nature to drive it back to what it was in pre-industrial time. So unless we can pull the CO2 out of the atmosphere, we're kind of stuck with carbon dioxide for a very long time. And that's a worrying feature of this. This is a corresponding graph for the Earth's mean surface temperature. And that's even more stark. Whatever temperature we have when we turn off the spigot, we're going to be stuck with for a long time. And that's why we think, yes?
Kerry, what's the, this slide and the previous two, what's the time frame that they're expecting that doubling to happen?
By 2050.
2050, okay.
Yeah.
Thus, such the focus on trying to be net zero by 2050 and all the
Exactly.
other 2050 benchmarks, okay. Got it.
Now, if we can figure out how to take the carbon out of the atmosphere, we can do we can reverse some of this.
Right, adjust.
Not all of it, but a lot of it.
Okay.
Is that something we're working on right now,
Yeah.
to try to figure that one out?
Yes, a lot of research is going on about that. We can do it, it's just way too expensive at the moment. So, one thing I'll say, and I'll drift into policy a little bit here, the big growth in emissions doesn't come from here. It comes from India, equatorial Africa. And unless we can either take the carbon dioxide out or create a clean energy source that's practical and economical for them, whether we like it or not, you know, what we do otherwise is sort of immaterial, it's symbolic. That's where all the growth is coming from.
And what about China as far as that's concerned?
That's another big source of growth.
Right.
So the implication that's seldom addressed is population, the
Yes.
amount of people in the world, because we always hear about the gases and the fuel emissions, et cetera, you know, raising the CO2, but in Population Connection, which is an organization, you know, it's like, it's not talked about.
This is not nearly, I agree with you, it's not nearly talked about enough. The other interesting thing about this is feedback. In the last 40 years, the civilizations that have controlled their population, like China to some extent, have done so by greatly increasing per capita energy consumption. It's a key. You make people wealthier, right? They burn more carbon. And their population. So the population, the key to lowering population, according to people who study that, is to actually make people better off. They have fewer children. Women are better educated. There are all kinds of reasons for that. So if you say you can't burn coal, because we told you not to because it's bad, and the consequence of that is they stay energy poor. You know, there are 800 million people today with zero access to electricity. Isn't that amazing? If you keep them poor, they're going to keep the population growing very fast, because children are wealth in that kind of economy. And that works the wrong way for greenhouse gases. So you're in this trap, right? And the only way out of that trap is develop an energy source that really makes economic sense, that will enable them to grow without putting pollution. And that's something we haven't really done. But maybe we will. I hope so. That's the real problem right there. We can do things to protect our towns, as all of you are doing, but in terms of reducing carbon dioxide, it's really about those growing countries.
Thank you.
Well, I don't want to, I'd like to get into the question and answer session, so I'll just go through some of these quickly. The known risks, as you all know here, increasing sea level is one. It's not uniform. It changes over time and it changes in different places. It's very simple physics to show that when you warm the atmosphere, rainfall can be much more intense, but it has to be less frequent. And again, it's a science story for you that I'd love to tell you about someday. But ironically, it means we expect more droughts and more floods. And in fact, as we know, we're going to see that here. There's more heat stress and other health risks related to temperature. And what our DoD is worried about is the propensity of dislocations caused by water and food shortages to put a lot of pressure on people to emigrate from their native lands. And this historically has led to armed conflict. And you can see that beginning to happen. That's what they're worried about. That's what keeps me awake at night. But we also have to be fair that there are benefits. There's some increase in plant productivity when you put CO2 in the atmosphere. And there's a big reduction in health problems related to cold. Okay, so we have to add all of these things up. But as I mentioned at the beginning, we're so beautifully adapted to the climate we used to have that any change is bad in the net, and this is no exception to that. So the IPCC says when you add it all up, there's likely to be a significant increase in damage. Notice they don't put a number on that. All right, I want to just end with a discussion of one of the climate risks that I have to work on professionally, which is hurricanes. And so I'll just run you through a few. Big hurricanes are very rare in New England. We've only had a handful of big ones, and I'm showing them to you. Beginning from the first one that was really recorded was the big 1635 hurricane that came up the coast in my little fishing village in Maine. It ran a big sailing ship aground in the harbor where I happened to keep my sailboat. It was a very interesting history. The captain got all the people off the ship with no loss of life, but there was a lot of loss of life on other ships. That was probably a Category 2 or 3 hurricane, and the most recent really big storm is the 1938 storm. When I first started giving these talks in the 80s, there were people who remembered that. It became very scarce. That was a huge catastrophic, killed more than 600 people in New England, and took down something like 30% of all our forests. So if it happened then, it can happen now. They're rare, but they're very destructive when they happen. This is a painting of downtown Providence in the 1815 storm. Okay. Providence is a city of duck, unfortunately, for this kind of flooding. Here are 24 tropical cyclones, which is a generic name for hurricanes of all intensities, that affected New England in the last, after 1850. So on average, we have once every 7 years or so. At MIT, we learned how to produce synthetically from models of hundreds of thousands of hurricanes. It's a long story I won't bore you with. And when we do that, we can really get a much better handle on hurricane risk. Basically, we're embedding very, very detailed hurricane models within the coarse climate that's being simulated by global models. It's a long, long story. But the bottom line is that we get a pretty good handle on hurricane risk today and in the future. So here's an example of just 100 tracks out of 6,000 that we generated from 8 global climate models over the period 1985 to 2014, all of which were chosen to be tracks that affect New England. So the point is that we can get around the statistics of low numbers by just doing massive amounts of simulation. The colors on this diagram are an indication of how strong the winds are. These are the 100 top, now this is a randomly selected 100. And so I did this for the town of Winthrop for you guys. This is my last real slide, you'd be happy to know. And it just shows the annual frequency of winds right in the center of Winthrop as a function of how strong that wind is. So on the bottom is wind at miles per hour, 40, it's hardly anything, right? 60, 80, up there. And this is frequency, annual frequency. You notice that this is on a scale that's very nonlinear, so this is once every 4 years, this is once every 40 years, once every 400 years, and so forth. The blue is for the period 1985 to 2014, and the curve with the dot is the average among these 8 models. And the shading is the scatter. It's a measure of what we don't know. Okay? It's a lot of uncertainty there. The red is exactly the same thing, but for the period 2071 to 2100 under a kind of a middle-of-the-road emissions projection in carbon dioxide. And you can see there's much more scatter. So the future, predicting the future is pretty hard compared to predicting the past. And so that means, for example, that on average, most of these models, a wind of 70 miles per hour would occur in Winthrop once every 200 years in the climate of the recent past, which is too frequent in a way. You want to be prepared for that, even though it's fairly rare. But by the end of the century, it might be every 50 years. There's a big change in that. And that's the kind of work we're doing to try to put some numbers with the uncertainties on this. And of course, we do this all over the world, not just here. This is exactly the same thing, except this is rain now. The total amount of rain that falls during each hurricane in inches and the same thing frequency, but you see an even larger climate effect. Simply because hot air holds more water than cold air. That's really the physics there. So you get 3 inches of rain from a hurricane almost never here because the hurricanes are moving so fast. 3 inches will flood your streets, but won't be irreversible damage probably. But 3 inches would happen every 40 years or so in the future. And then you start getting not trivial risks of much more rain. So this is how we're trying to go about quantifying. So let me wrap up. Several aspects of our science are pretty well established and have been for a long time, and not based upon computer models, but just simple physics. The Earth's climate, I didn't mention this to you, doesn't run away like it did on Venus or Mars, where either the ocean's evaporating and gets incredibly hot like Venus, or the whole place freezes over. We don't go into those extremes. But within those bounds, there's a strong sensitivity to things like how much sunlight's coming into the planet. Climate science is pretty well established. A lot of the general points I talked about were well known by the end of the 19th century. The Earth's greenhouse effect triples the amount of radiation absorbed by the surface, owing to the presence of a tiny amount of trace gases, the most important, which is CO2. Remember, water vapor is more important, but it's a feedback. It just responds. Simple models predict that you're going to see about 3 degrees per doubling CO2, but with a lot of uncertainty around that. Okay, that's sort of our best shot at it, but there's a lot of uncertainty. The long atmospheric lifetime of CO2 limits the amount of time in which we can do anything. That's just a scientific point. We can't just go back to normal very quickly. We're altering the atmosphere, I would argue, at considerable risk to ourselves and future generations. The change is mostly felt through extreme events like droughts, wildfires, storms, and so forth. And although there's still a lot of disagreement among climate models, they're fairly clear indications that we're going to experience more hurricane risk in New England, alas. I wish I could end on a happy note. But we're all here, and Winthrop is here, so we have to be grateful for that. Thank you.
Thank you very much, Professor. I would take some questions and I'll relay them. I may repeat some of them in order to help the TV out there. I also want to make sure if you haven't visited the table back there to enjoy some snacks. My name is Paul Baskin. I'm with the Winthrop Working Together group as well. Anybody have any questions? Yeah, go ahead, Tom.
You talked about climate change and hurricanes.
Yep.
Can you talk about climate change and nor'easters?
Very good question. That's exactly what we're working on now. We're very far behind on that, which is surprising because there are a lot more winter storms than there are hurricanes, particularly up here. But it's a big technical challenge to do that. We are making progress. If you invite me back in 5 years, I'll probably be able to tell you something. It's right in the middle of our research, collectively all around the world. It's a very important problem. I know because the town I live in got hammered by nor'easters. Well, actually, they weren't nor'easters, they were southerly storms, but they were winter storms on the coast of Maine this year.
So if the sea level is rising a little bit, is it
Yeah.
rising?
Well, in
I
most
know that
places,
it's uneven.
it's uneven, yeah.
But it's rising, is it rising here? Like
Yes.
in Boston Harbor, like in the ocean?
It is.
How much of a rise did we have, or are we having currently?
Well, I actually have a chart showing, it's very slow. It's like a millimeter per year, thereabouts. It's not even less than that. Over a decade, it's about a centimeter a rise. So that's not very fast, and we're not really, if that's all we were doing, we'd somehow have time to cope with it. But there are indications that's accelerating, that it's projected to accelerate as the great ice sheets start to melt faster. Now, that kind of projection's got a lot of uncertainty in it too. So, it's not certain. The way that these, in practice, it affects us is not because an ordinary high tide is a problem, not yet anyway. It's the storms that arrive at high tide that are the problem. Yes.
So, is they a problem with the storms because they're more severe, or are they a problem because we are doing things that are contraindicated in sensitive areas like coastlines? For instance, if you look at like Newport, Rhode Island, the big mansions on the water, they were like 100 yards from the water.
Yeah.
Well, now we're building at the water.
Yes.
And I can think of several properties, with the Hunt that are literally on the water. So is in factor of that significantly so? Because
Very significant. In fact, the wholesale migration of people all around the world into dangerous places, mostly coastlines, is the big driver of increasing damage at the moment. The way I look at it is you have a collision of two things going on. The demographic thing you mentioned, people are moving to the sea, they're building structures right on the sea. All by itself, that would lead to big increased damage. And then this is being amplified further by climate change. So the answer is really both. Now, I don't want to get into a long song and dance, but the fact that we're moving to the coastline in the United States anyway is clearly related to the fact that inadvertently the government massively subsidizes people to move to coastlines by capping their insurance premiums, by bailing them out when they get flooded through FEMA flood release. It's a huge problem, right? And I could spend all night talking about it. So if you know a good bar around the world. But it is the big gorilla in the system. It's not just climate change, it's us. And we're moving into risky areas.
I'm a little bit confused, which isn't unusual, about carbon dioxide. You say you wish there was a way we could remove carbon dioxide from the atmosphere, but yet at the same time planting trees and greenery and cutting down on aerosols or whatever is being encouraged. Did you say there were two kinds of carbon dioxide?
Yeah, so far as there are two kinds, but they make no difference in terms of their effects on climate. But there are two kinds in the sense that what you get from burning fossil fuels is very slightly different from what you get from ordinary respiration from plants
And you
from
want
us.
the ordinary respiration
Yeah.
from plant carbon dioxide.
You do. You don't want to remove all the CO2 from the atmosphere for sure. We'd really be in an ice
But you
box.
don't want that sliver of toxic CO2.
You don't want it to increase too much because it changes the climate too much. It's not that it's toxic to us. Actually, if you put enough carbon dioxide, it would be, but you'd have to put in a whole lot more than we're talking about to affect your ability to breathe, for example. What we're worried about is the warming effect that it produces, the greenhouse warming.
But the plants and their carbon dioxide wouldn't affect the greenhouse.
It does, but in the natural system, it's balanced.
I
It's
see.
just the right, a Goldilocks amount of CO2 in the atmosphere.
Oh, no wonder I was confused.
It's not an easy subject.
Thank you.
Sure.
Hi, so I'm on the recently formed Climate Commission, so we've been drilling down a little bit on impacts of increased, tidal levels and that kind of thing. We've been looking at models, 2030, 2050, and, that's informing us that we can be substantially impacted by substantial increases in impacts and flooding, and we're already realizing some flooding here. Does the data point that we're only rising about 1 millimeter a year contradict those models, or how do they both coexist?
It's, a millimeter a year doesn't sound like much. It's a centimeter over a decade. And over 100 years, it's 10 centimeters, and that gets to be real numbers. So New York City, as you know, was flooded by Hurricane Sandy. If Sandy had happened, exactly that meteorological event had happened 100 years earlier, Manhattan wouldn't have been flooded because the sea level there was about a foot higher in 2012 when Sandy happened than it was in 1912. So yeah, it's a combination of the sea level rise and the change in the climatology of storms. But there are other things going on, right? It's not just that people are building houses closer to things, but when you put in certain measures to try to beat sand on the beach and so forth, they can have effects on currents. All the levees that they build to protect the city of New Orleans, when they're working, they work, but they actually cause floods in smaller villages in other places. They make the flooding much worse. So there's always a price to pay for that kind of geoengineering, if you will.
Yeah, let me just to follow that, I'm trying to understand, because I think I've heard estimates of the sea level rise much higher than what you're saying. Are we mishearing that somewhere?
No, you're not, because it's projected to increase.
Yeah.
That's about how much it has been, but it varies a lot in spaces. I probably go back. My own memory of these numbers is not all that great to show you what that chart said, because it actually had numbers on it, trends per decade. There we go. See that? Okay. Blow it up. Oh, no wonder you can't see it. There's no color scale on there. How did that go away? I'm very sorry. There should be numbers on that, and I'll fix it for next time, but I'm not going to give you a precise answer.
So that is, I was wondering about that, so that, the red versus the blue would be
Red is up
different
and blue is
decades.
down.
Yeah, different decades of what the,
Yeah, it's a trend over the, sorry? The orange is places where the sea level is going up. The
Why
orange
do
and
they
red.
keep saying the Gulf of Maine is changing temperatures faster than most other regions of the world?
It is, but this
I know.
this is temperature at sea level.
Why would that be?
We'd like to know that. The lobster fishermen want
I
to know
just saw
that
a whole
too.
Nova thing that Ryan Kerry made at the
I saw
aquarium
that
on
too.
the bay,
Yeah,
the
it's
Gulf
great,
of Maine.
great program, yeah. We don't know. There's a lot of speculation. There's an awful lot we don't know. Yeah. But we will someday.
So what are the successful methods of fixing carbon?
You mean extracting it? from
Yeah,
the atmosphere?
what are we doing that is working? You said there were some methods that work but are too expensive.
So I visited the operation a few years ago in Iceland. They were trying to do this. And CO2 strongly reacts with basaltic rock. And the net result of that reaction is limestone. Limestone's a hard rock. If you tie up the carbon dioxide in limestone, it isn't going to go anywhere for a very long time. And they're doing it, but not at anything like the scale that's necessary, and it's very expensive. But if you don't try, right, so you can put some, the people who work on it are not very optimistic about driving the price down. But there's an awful lot of research. If somebody comes up with a good way of doing it.
Like the vacuum clean whole thing they were talking about.
Vacuum cleaner.
NPR talks about this all the time. They're gonna suck it out of the air.
What about just the idea of the volcanic effect, of just putting up a lot of stuff in the sky to blocks with that? Is that not?
That doesn't attack CO2. It masks the effect by reducing sunlight. And we have done the experiment, or nature did it for us, when there's Mount Pinatubo blew up that put a lot of sulfur in the stratosphere, and it did cool the climate. The problem is that there are a lot of problems with it. One is that it affects the climate. Even if you try to drive the temperature down, you're also changing other variables, like you're driving rainfall down below what it was in pre-industrial times. And if you stop doing it, in a few weeks you're in really bad trouble because you're sort of committing yourself to it always. And there are unknowns there, so it's risky and not too many people. The problem is that, you know, a billionaire today, literally a billionaire, could do it on his or her own, go out to some island and just start doing this. There's not much by way of law to stop that. So we could write all kinds of great fiction stories that might turn out to be true. Colleen?
Methane.
She wants to go.
Oh,
Yeah, I know there's been two things, because we're thinking of the Gulf of Maine, when we think about it. I know there's been some, I forget exactly the word for it, but it's instead of putting things in the sky, you put it in the ocean. It's like iron and stuff. Has that been anything that's been, what thoughts on that, or?
I think you're talking about iron filings
Yeah,
put in the
yeah.
sea. So the idea behind that is really quite interesting. And that is there are phytoplankton and other organisms that naturally take CO2 out of the water. And their abundance is limited by other nutrients in the water, among which is iron. And by seeding the ocean with iron, you would create phytoplankton blooms that take carbon out of the atmosphere.
But that wouldn't put it in something like limestone, it would just be in the ocean.
Well, some of it would ultimately end up in something like limestone, a little fraction of it that gets buried on the sea level, but that takes a long, long time compared to what they're doing in Iceland. The other problem that they discovered when they actually tried to do the experiment, not in the Gulf of Maine and somewhere else, was that the abundance of phytoplankton quickly became limited by the shortage of other nutrients. You know,
So too much, essentially, that it just.
yeah, it gobbled up the iron, but it was starting to be limited by phosphate or something. Yeah, go ahead.
I keep hearing about methane. Where does methane fit in?
Well, that's a good question. So methane is actually a far more powerful greenhouse gas than CO2, but it's far less abundant. So in the grand scheme of things, but we're putting a lot of methane in the atmosphere as well, and it does make a difference. One qualitative difference is that its residence time in the atmosphere is measured in decades rather than hundreds or thousands of years, so it goes away more quickly. Doesn't mean we shouldn't pay attention to it, but it's something that cleans itself up on a somewhat faster time scale than CO2, fortunately.
Maybe it's just me not paying attention in science class, but I always thought the order of mountain gases was nitrogen, oxygen, then carbon dioxide. I had never noticed that there was this sliver of argon.
Right.
What is the argon? What what is argon even used for? What is
Nothing.
the, yeah,
It's a very inert
It's an
gas.
inert
Well, I don't
gas.
know about nothing. I'm not.
I've never heard of.
It's used in the wine industry to top
Yeah,
up
we don't
bottles.
teach about argon.
Because it's
I used to work in it, yes, that's how we used it.
Well, that's a very important, I have to say that's very important. I stand corrected.
I never mentioned in school, because I've been in environmental science and environmental bio classes, and no one ever talked about argon.
That's right.
Never once.
It's a inert gas, and aside from its use in wine preservation, it's,
Poor lobby. Yeah.
Go ahead.
I think she
Oh, I have a question via text message from Clara, who's the one that's working together. She said, she wants to ask about the specific situation, our specific situation near the airport and what's the extra impact for us being at the airport, if any?
I don't know. I think when it comes to climate impacts of jets, it's a global thing. It's
Yeah.
not really local. When it comes to air pollution, I don't know the answer to that. Certainly they are putting other gases and particles in the atmosphere. Whether they're close enough to the flights and they're low enough, I don't know the answer to that. It's a good question, but I'm not the right person to ask that.
They are close and low.
Yeah, I noticed
Many
coming
years.
in.
Yeah, coming in,
I
yeah.
suppose that's the Air France flight. It was on just last spring. 5:30 to Paris, I know that flight.
Sure.
We've all heard that cows emit a lot of methane, but I heard recently that growing rice emits a tremendous amount of methane. And I wondered if all the rice that is produced in the Orient is having a noticeable effect on the amount of methane.
It is. It's now regarded as the #1 source of methane, anthropogenic source
So
of rice cultivation.
are people trying to switch those
They're trying
folks
to come up with,
something else?
yeah, they're trying to come up with other strains of rice that aren't quite so bad this way, but frankly, I don't know where they stand on that. But if you switch from red meat to rice, you're going from the frying pan to the fire. Yeah, sad, isn't it? I like sushi too.
Are there other sources, big sources of methane that maybe we're not commonly familiar with?
One that we're worried about is melting of tundra releases methane into the atmosphere. The latest studies I've seen on that suggest that while it's true, it's not all that much, but there have been estimates in the past that there's a ferocious amount of methane tied up in tundra. And so if we start, because of global warming, starting to melt tundra, it's releasing methane in the atmosphere. There was a huge explosion of methane, I think, in Russia somewhere a few years ago. Or maybe it wasn't Russia, but it was just because so much methane had accumulated just under the surface, and something lit it off, and there was like a bomb going off.
We should probably wrap it up pretty soon, but Carol's got another one, maybe, yeah, go ahead. Oh, there are two more, okay, we'll get to it, go ahead.
My question is, what's the percentage of methane that's in the atmosphere from household appliances? I know that's one thing that's been talked about in the state is changing from stoves, things like that.
Don't know the answer. It's a good question. Yeah. I haven't heard that before, but I can imagine why it might be important.
Tom?
Can you talk about the changes in ocean currents, particularly the conveyor belt?
Yeah, that's another, this whole science is so unbelievably interesting, and I feel like I'm just skimming the surface. That's another great question. So, the problem is it's very hard to measure the ocean compared to the atmosphere. You put a probe down, you can't radio information through water. You have to use acoustic signals or just a probe that you can haul back up. And so it's very difficult to measure ocean currents. What few studies exist suggest that I should mention that we do know that the ocean is transporting a large quantity of heat from the tropics to the high latitudes, and that's a very important part of the climate. If you took that away, we'd have a very different climate. And there is some indications, a lot of this northward heat transport by the world's oceans occurs in the Atlantic specifically, even though it's a small ocean. And there are very interesting reasons behind that. But there are indications that this transport's slowing down in the Atlantic, which would cause the equatorial Atlantic to heat up a little bit and the high latitude Atlantic to cool off or at least not warm as fast. And there's some indications of that, but it's something we worry about. There are a lot of studies, the models are all over the place on this, and we have a hard time. We're the biggest and most exciting improvements are in how we're measuring the ocean. That technology is getting better every day, so we'll eventually be able to do it.
I'm going to jump, squeeze one in since you mentioned that. What would be the, if that conveyor belt were to stop, how do you think we would feel it here?
Well, one thing is we'd have more hurricanes, actually.
What
Hurricanes. Probably not very much effect on temperature because we're sort of at a node in that. But there was initial concern that it could collapse, and it has collapsed in the geological past. We know it's capable of collapsing, but nobody really thinks it's going to go that far.
I just wanted to say thank you for coming. Two of the takeaways I had from your presentation. One was, I think there was a debate for a while that's probably not as much of a debate anymore, but whether or not climate change is natural or man-made. And you very well answered the question. It's actually both. It is a very natural cycle, but we interrupted it with the industrial age, so that was helpful. The other thing is when you talk about numbers, it can be tricky to wrap your head around it. Because when you had the slide on that talked about the curve and the likelihood that there will be about a 3-degree warming between now and 2050, and anything beyond 4 would be catastrophic. I think it's hard sometimes when we hear about a 2-degree increase, we're thinking there's not much difference between a 70-degree day and a 72-degree day. That's not what we're talking about. That this is a significant increase. The other thing I was going to mention is we've done a lot of work. We had our climate commission meeting the other night, and we had Connor from Woods Hole come in. His group was charged with doing we had got a grant, and his group did a study specific to Winthrop on the events that we can expect. That was the other thing I appreciated that you focused on. It's not so much about specific year-over-year rise. It's more about the frequency and severity of events. So he was really mapping out for us what's happening, most likely to happen, even in the next 5 years, and starting to quantify the financial impact to Winthrop, which is significant. So you've clarified a lot, I think, of the foundational climate dynamics going on that's driving all of that. And then there's the entire other conversation. What do you do about it? And that becomes a financial, political exercise.
Yes, it does.
Yep.
Well put.
So thank you.
Thank you.
I have one just small hint question. What is one thing or the one thing as an individual that you would recommend? What can we possibly do besides get together and have these discussions?
Well, you're asking me a question that's really outside the field of science, so I'm just going to give you an opinion that shouldn't count for very much. As I think we've gone beyond the level of what individuals can realistically do that really makes a difference. It's collective action that we have to engage in. And we have to get young people. The question you asked is a question that I get very commonly from young people. What can I do as a person? And there are things you can do, but they're pretty small in their effect, even if you add them up, changing light bulbs, whatever. But it's moving the world at the scale of nations and maybe states and certainly towns. That's where it starts to make a difference. And it's not really happening a lot. There's a lot of posturing going on and a lot of things, I think wishful thinking, like we were going to go 100% renewable. There's no math I've ever seen that suggests that's possible. And we won't face the music on that because of ideology. I mean, there's a lot of things that get in the way. I mean, France and Sweden are 100% non-fossil fuel electricity and have been for several decades. Nuclear power. They do it, we don't. We don't do it anymore. Why? You know, we do actually have a technical solution, but people don't like it. And that makes a difference.
Thank you, Professor. It came a long way for this, and I'm really good.